Welcome to The Explainer. Today, we're going to trace a line from something super simple, like the ache you get from a heavy backpack, all the way up to the unbelievable spinning force of a cyclone. So let's dive in.
Okay, so what do a backpack, a water pipe, and a totally devastating cyclone have in common? I know, it sounds like the start of a bad joke, right? But think about it. What could possibly connect those three things?
Believe it or not, they all follow one simple, fundamental rule of physics. It's this single idea that explains how forces get spread out, why water moves the way it does, and how the air itself behaves. And once you get it, I promise you're going to start seeing it absolutely everywhere. All right, so let's kick things off with something we've all felt. Picture this. Two siblings, Mega and Pawan, are heading to a picnic. Now, their backpacks weigh exactly the same, but one of them is really struggling. Their shoulders are just killing them. The other one, totally fine. So what gives?
Well, it's all about the backpack straps. See, Pawan's bag has these really narrow straps, and they're just digging into his shoulders, concentrating all that force onto one tiny spot. That's high pressure, and yeah, it hurts. But Mega's bag, it's got these nice wide straps. They take that exact same weight and spread it out over a much bigger area. The result? Way less pressure and a much happier walk to the picnic. And this simple story gives us the magic formula for today. Pressure is just force divided by area. Think about that. For the exact same force, if you shrink the area, the pressure goes way up. If you increase the area, the pressure goes down. It's this simple trade-off that's going to unlock everything else for us. And the funny thing is, we use this principle all the time, probably without even thinking about it. Why does a nail have a sharp point? To create massive pressure and drive into wood. Why is a knife's edge so thin? Same reason, to slice through that apple. And hey, ever see someone carry a heavy pot on their head using a coiled up cloth? That's them cleverly increasing the surface area to make the load feel lighter. It's physics in action, every single day.
Okay, so that makes sense for solid stuff, right? Backpacks, nails, got it. But what about liquids? Well, this same idea explains something you've probably seen 1,000 times. Why are water tanks always stuck way up on top of buildings or on their own tall towers?
Let's imagine a little experiment. Say you take two pipes, one wide, one skinny. You stick an identical balloon on the bottom of each one. Then you fill them both with water to the exact same height. Now you'd think the wider pipe, the one with way more water in it, would make its balloon bulge more, right? Nope, they bulge out exactly the same. But here's the kicker. The second you add more water to one pipe, making the height of the water taller, its balloon instantly stretches out way more. So the big takeaway here is, it's not the width or the volume of the water that matters for pressure, it's the height. The taller the column of liquid, the greater the pressure at the bottom. And that right there is why we put water tanks up high, to get that height and give you good water pressure in your shower. It's also why the bottom of a dam has to be massively thick. It's got to withstand the incredible pressure from all that deep, deep water pushing against it.
Okay, let's take another big leap. We've done solids, we've done liquids. Now let's talk about the gas that we're all swimming in right now. The air, our atmosphere. You can't feel it, it seems totally weightless, but it is pushing down on you with an unbelievable amount of force.
No, seriously, get ready for this. If you take an area that's just 15 by 15 centimeters, so smaller than your average dinner plate, the weight of the air pushing down on just that little square is about 225 kilograms. That's like having a huge motorcycle just sitting on your head right now. Wild, right? So that brings up a pretty obvious question, doesn't it? If the air is that heavy, why aren't we all just squashed into pancakes? Why don't we feel a thing?
The answer is actually pretty elegant. It's a perfect balancing act. You've got all that atmospheric pressure pushing in on you from every single direction, but at the same time, the pressure from the fluids and air inside your body is pushing out with the exact same force. They cancel each other out perfectly, so you can just walk around totally oblivious to this cosmic squeeze.
But what happens when that perfect balance gets disturbed? When the pressure isn't equal anymore? Well, that's when things get interesting. Nature has a very powerful way of trying to even things out again, and we call that response wind.
And this right here is the fundamental rule for all of this. Air always flows from a place of high pressure to a place of low pressure. Always. It's why air hisses out of a punctured tire or why a balloon zips around the room when you let it go. Nature absolutely hates a pressure imbalance, and it will do anything to fix it.
So how does this create the wind we feel every day? Well, it all starts with the sun. The sun beats down and heats up the land. That, in turn, heats up the air right above it. And what does warm air do? It gets lighter and it rises. And when it rises, it leaves behind an area of, you guessed it, low pressure. Well, the cooler, denser, high-pressure air from all around sees that empty spot and rushes in to fill the gap. And that rush of air, that's wind. Okay, so it follows that the bigger the difference in pressure, the faster the wind is going to blow, right? So what happens when that pressure difference gets really, really extreme? Well, that's when we stop talking about breezes and start talking about storms. Now, here's a weird twist, a really counterintuitive idea. Really fast-moving wind actually creates an area of lower pressure. You can try this at home. If you hang two balloons side by side and blow really hard between them, they don't fly apart. They actually get pushed together. That's because the normal air pressure on the outside is now higher than the pressure in that fast-moving jet of air you created. Now scale that up. When a massive windstorm blows over a house, the pressure above the roof drops like a rock. But the normal higher pressure inside the house is still there, and it pushes up, sometimes with enough force to literally lift the roof right off. A thunderstorm is basically this whole process on steroids. You get this powerful updraft of warm, moist air, creating this intense low-pressure chimney. As it rockets upward and cools, you get these huge, towering clouds. And inside those clouds, it is absolute chaos. Water droplets and ice particles are slamming into each other, getting tossed around, and all that friction builds up an insane amount of static electricity. At some point, that charge has to go somewhere, and boom, it discharges as a bolt of lightning. That lightning bolt is so hot it instantly creates a shockwave, which we hear as thunder. And as powerful as a thunderstorm is, it's not always the end of the line, because under just the right weather conditions, these storms can keep growing and develop into cyclones.
And here we are, the ultimate storm, the cyclone. This is what you get when you take every single principle we've talked about, pressure, heat, rising air, and you put it all together over a warm ocean, creating a spinning giant. So how does this monster get started? Think of it like a giant feat engine. It all begins over warm ocean water, which warms up the moist air above it, causing it to rise. Now here's the key. As that water vapor rises and condenses into clouds, it releases a tremendous amount of heat. This heat is like pouring gasoline on a fire. It makes the air rise even faster, which creates an even more powerful area of extremely low pressure at the surface. So air from all the surrounding high-pressure areas comes roaring in to fill the gap. But because our planet is spinning, that air can't just go in a straight line. It gets deflected and starts to spin, winding up into this massive rotating storm. And the structure of these things is just incredible. Right in the middle, you have the eye of the storm. The pressure there is the lowest it gets. But strangely, it's calm. The skies can even be clear. But don't be fooled. The real nightmare is the area right around it, the eye wall. That's where you find the most violent winds, sometimes over 250 kilometers an hour, and the heaviest rain. It's the most dangerous part of the storm, where all that air is spiraling upwards with incredible force. So there you have it. We went from a sore shoulder to the very heart of a spinning cyclone, and it was all driven by one simple idea, pressure, which leaves us with one final thought to chew on. We know you need heat and a pressure difference to create the wind, but if the Earth suddenly stopped rotating, would that simple act of warm air rising over the ocean still be enough to create a cyclone? Or does this engine of destruction need that spin to exist at all? Thanks so much for joining me on The Explainer.